Alright, time for another dryphysics.com video presentation. Yes, the Wikipedia sucks. And no one cares. Unfortunately, these videos are viewed by so few people that it's really not much point. And, the future could probably find some use for them maybe, but there's probably going to be simpler, shorter videos that'll go over the same material, so in some ways it's probably quite useless. But anyway, yeah, I can only do my part. So, yeah, so we'll do some more on force. And, but it would be nice if somebody would challenge. I mean, it's not that hard to challenge a Wikipedia page. They have little buttons on top of the page that say edit. You just click the button. And then there's a talk section, which is a lot safer. So at the top of the page, it has this nice little thing that says talk. And you just click on that. And you can either make an account, so you have a screen name, or you can just use your IP address that they'll just display you as an IP address. Which I don't see much harm in. Somebody can't really do anything with it. But anyway, so we're at the point where the document says the precise ways in which Newton's laws are expressed have evolved in step with new mathematical approaches. So somehow they're evolving Newton. I mean, I wish you could do that. I mean, I wish we could evolve the Bible to turn into something rational. That would be really nice. But no, it doesn't evolve. So they say the Torah is evolving, but I don't see that happening either. Frankly, they still haven't figured out that there's no point in torturing animals, to make your food safe. And no, you don't have to torture them to do that. Anyway, just really, it's just so stupid. So much stupidity in the world, really. Just so depressing. All right, so I guess instead of getting right into it, we'll just talk a little bit about force and just get rid of it. Thank you. Don't show it twice. And explain. So Newton believed in 3 dimensions. So that's sort of the important thing here. And he believed that space was a continuous stuff that had positions in it, in solid positions. The positions didn't change. Okay, there's just a place in space, and everything is just moving its position in that space. And the stuff moving is all just momentum. It's just everything has a mass, okay, an amount of substance, and the substance is moving at velocity. So, maybe it could be SV, if mass confuses you. And that's all that there really was. So if there's a force, okay, somewhere, okay, and it's acting, I mean, I would argue that, the only way you can really understand the force is as something with a vector, it's some sort of thing, some sort of mass moving, a little one, okay, with a velocity. It's a bit of force or whatever. The stream is made out of molecules of water, it's stuff moving. And that forces are stuff moving. It just happens to be moving really fast, and it happens to be really invisible. So you can't see it, but it's a force moving, and somehow, okay, a matter actually acquires the force. That is, the force ends up being in here. The force doesn't go through it and come back out. The force doesn't, it has to be used. It can't, the light can't be absorbed by an object and reflect. And it can't, and it can't, it can't keep going. It can't give the thing energy and the light continues to go. It can't do both things. It either gets stuck in an object or it doesn't. And the same kind of thing, it just kind of proves it with the Newton's cradle, is the simple idea that, this one has the force, and obviously it hits the other thing, and it either gives all the force or some portion of the force depending on what the mass is. If they're same mass, then the force just goes from being in here, and it just goes to being in here. And now this thing does exactly what this thing was doing. So the force is a substance, it's a stuff, and it's transferred between objects. And the only thing that makes it a little bit complicated is that, you can have a force and it can be interacting with some other much more complicated surface, that is a surface that has lots of different kinds of things in it. All right, and it can be moving things of different size. So as it interacts, it can be giving little pieces of energy for little things, and it can give little bits of energy to another thing. And depending on how big it is and how much velocity you can give it, you can dispense with a lot of your energy. You can have a certain amount of force, and you can just give away little pieces of it to the ground, for example. And the force that's in you goes into the ground. So that's happening to us all the time. Gravity goes into us, gives us momentum. Our momentum pushes into the ground, right? I mean, you're sitting on the ground, and what you're standing on the ground, let's just say. And what's going to happen is, well, the force goes into you. It gives you momentum. You move into the ground moves. It takes the force away. So the force all leaves going down into the ground. Okay. And the fact is, when you add that extra force to the ground says, I got too much force. I already have a whole bunch of force here. I already got a whole bunch down here. So I'm all full up. And it just rejects it and pushes you back up. Okay, and so you just keep pushing down, and the gravity, the ground pushes you back up, and the gravity pushes you down. And it's just an exchange of force. You just keep putting pressure into the earth. Okay, the earth pushes you back, all right, but it's still overpressurized, right? You've added new pressure to it by standing on the earth. You're constantly adding new pressure. All right, but yeah, it has to be exchanged. I mean, it's collected. Force is collected by objects. And then two objects could have the same amount of force going one way, like they both have an arrow going that way, but they can still exchange, because this one's going to have some energy going in this direction, some portion, and now they intersect, and it can exchange the part that's different. So the parts that's different, they can exchange. They can't exchange stuff where it's going the same way. That's like the same pressure. So, and collisions, for example, direct collisions, you got to be able to add up the fact that it's all real energy. Movement is energy. Any movement in space is energy. You can't have unenergy. There's just energy. There's not unenergy. So if you understand Newton's three-dimensional universe, and there's 2 points, A and B, okay, and they're places in the universe, and one thing happens to be going this way, and another thing happens to be going this way, the fact is those are real motions compared to a fixed space, B, and a fixed space, A. These things are really moving. B, this thing's moving compared to B, and this thing's moving compared to A. It's no doubt about the motion, and they really contain force. And so the only option is when they collide into each other, if we say they're inelastic, they're crushable, then they're going to crush. If I put something between them, you know what's going to happen. The two forces will come in, they'll apply pressure, and they'll crush it. All right, they'll cause it to change its shape, okay, and they'll cause energy to move, and they'll cause it mostly in terms of how the energy is eventually dissipated, is that first it moves the clay around, and then it's dissipated as heat, okay, radiation, photons of radiation. Okay, that's how it's going to get rid of the energy that you put into it. That's where it's going to turn into. So two big things are going to collide, and a bunch of little things are going to pop out, all right, and they're going to have the momentum. So a bunch of millions of little things will have a little tiny bit of force, and where you started with two big things that had the force. Now if you make them elastic, that is, they can't crush anything, they can't do any work, they can't convert it into any kind of radiation, right? Now we can make it into that, right? You can take two steel balls and smash them together and force them to stay together, and then you will create a bunch of radiation. You can burn a piece of paper. You can actually start a fire by just smashing two pieces of steel together with, flammables in between. Difficult to actually start a flaming fire, but it depends on what kind of paper you hit. But the fact is, you can create an awful lot of heat because the energy has to be dissipated somewhere. The force has to go. If you don't let the force reflect, then the force has to stay where the contact happened and just keeps repeating it until it vibrates enough atmosphere and enough other things to get rid of it. But let's say I just crashed them and they're elastic. Okay, they're steel or they have a spring. It doesn't really matter. What's going to happen is that the force has to keep going. This force is real. This force is real. If you're not going to make little things fly off, if you're not going to exchange the force with anything, then they have to leave with the same force going this way and the same force going that way. That has to happen. They can't change the facts that you have a certain amount of energy going in a direction, and here you have a certain amount of energy, and it can't cancel. So it either crushes something or it reflects. But there's no other choices. Now, they never get to that in the force document. They never explain any of that. Physics. And then they just vaguely reference some idea that there's some mv squared somewhere in this, which there isn't. Okay, 1,000 atoms going 1 mile an hour is the same ability to move little stuff. If you all you want to do is move little boxes, 1,000 people going 1 mile an hour will move just as many little boxes as one person going 1,000 miles an hour. The same number of little boxes will be movable. The same bowling pins will be knocked over. If it's knocking over bowling pins, and you just say that the pin's velocities can be exchanged, it's like dominoes or something. So you can hit a pin, make it go very fast, but it'll hit other pins and eventually dissipate into all the pins. It'll just move 10 miles an hour. And the fact is, the one person moving 1,000 miles an hour versus the 1,000 people moving 1 mile an hour will cause the same amount of motion in the pins. All right. So leave us go to what they wrote, which isn't really on the subject. So we know that Newton's all about momentum. Okay, they should just have the quote right there: twice the force, twice the velocity. 3 times the force, 3 times the velocity. But they don't make it that clear. But they make it pretty clear it's about momentum. But why are they saying it? Because they don't believe in any of this. See, I mean, the precise ways in which Newton's laws are expressed have evolved in step with new mathematical approaches. You can't evolve mv into 1/2 mv squared. It's not a rational evolution. They're completely contradictory statements about the reality. You can't do that. All right, so anyway, Newton's first law of motion states that, I don't know why they just don't link to the first law article. Why are they just doing these paraphrases? All right, states that the natural behavior of an object at rest is to continue being at rest. So it's just kind of baby talk, right? Obviously, if you don't catch the plague, you don't have the plague. You know, so why would you say, oh, well, it's the nature of an organism not to have infections? Yeah, until it gets infected. Yeah, right. I got that part. Okay. I mean, I don't have a heart attack till I have heart disease. You know. Well, there's lots of ways you can have a heart attack. And the natural behavior of an object moving at a constant speed in a straight line is to continue moving at a constant speed in a straight line. So again, it's all just baby talk. Of course, that's the thing. Everything is in a state, and its state doesn't change until something interacts with it. So this is just the requirement that there be an interaction for there to be change. That's what the first law is basically saying. There needs to be interaction for something to change. Nothing changes unless there's interaction. What causes interaction? Well, obviously motion causes interaction. Things move and they end up banging into each other. They try to move through the same space at the same time. And that's an interaction. Yeah, so it doesn't work. All right. The latter follows from the former because the principle that the laws of physics are the same for all inertial observers. So again, this is not Newton's statement. Okay. I mean, this inertial observer crap isn't something. Newton basically started the book by basically saying, look, it's just 3 dimensions. There's no other way to look at it. You could pick any point in space and just say how far is something from that point in space and how fast is it moving relative to that point in space. And that's all that matters. That defines what something's character is. Okay. All observers who do not feel themselves to be in motion, so this feeling part, again, is just such nonsense because it depends on how the force affects you. You can't feel gravity. No matter what gravity does to you, you'll never feel it because it's going to move every one of your atoms collectively at the same time. close enough to the same time that you can't tell the difference. You can only tell that you're moving because one piece of you moves and another piece next to it doesn't move. That's how you feel something. You can't feel something unless there's a difference in how some pieces of you are moving. All right, so it's just kind of it's a biology lesson. That sometimes the force hits you, can hit you right here, and now the force has to be moved through the rest of your body through chemical reactions. It's not force anymore, it's a bunch of chemistry, a bunch of atoms have to move. It's a completely different than what gravity is doing. So getting hit with a hammer is different than getting hit with a same momentum in the form of gravity. Gravity will move everything. The hammer will move this stuff where you hit more than it'll move your feet. A lot more. An observer moving in tandem with an object sees it as being at rest. So again, this isn't Newton's stuff. So its natural behavior will be to remain at rest with respect to the observer. Again, this natural behavior is just nonsense. It has to interact with something. It has to interact with photons, gravity, magnetism, or it has to interact with another physical object. Which means that an observer who sees it moving at a constant speed in a straight line will see it to continue to do so. Again, an observer's in a position in space, and it's just always an absolute position. You can't change that fact. All right, and clearly, yes, you can have a position in space where you get information from objects at a different time. That doesn't mean the objects produced the information at different times. It means that they are different distances from point B. So the information from point B gets to you sooner than the information from point A. Then there's no surprise there. You haven't bent anything or broken anything. I mean, they always have to interject this relativity crap and the stupid Einstein crap into every single subject. They have to destroy having a conversation about mechanical physics and turn it into a bunch of mush. All right, second law. According to the second law of motion, so this is the important one. This is where he clearly states it's about momentum. All right, he clearly states twice the force, twice the velocity, 3 times the force, 3 times the velocity. Not any notion, okay, that there's 4 times the energy or 16 times or 9 times the energy or 16 times the energy or 25 times the energy. None of that exaggeration. According to the first law of motion, at a constant speed in a straight line does not need a cause. So again, this is where did Newton say that in the first law, that you don't need a cause for motion? Of course, it just seems kind of silly. It is change in motion that requires a cause. Obviously, the Earth acquired its motion through causes. All right, it'd be idiotic to say the Earth had velocity innately. It didn't have any innate velocity. It had to acquire it impact after impact after impact, and through how it transitioned, through its existence, and it acquired its end velocity pieces at a time. But it obviously was caused. All right, anyway, it's just too silly. And Newton's second law gives a quantitative relationship, quantitative relationship between force and change in motion. Right, so he clearly states that momentum is motion, and your motion is equal to the force that creates it. The force is the momentum. It gives you momentum. Newton's second law states that the net force, so I understand the word net here is just so dangerous, because they say net and then they'll say per second. Per second isn't net. Okay, net means when you're all done. It doesn't mean per second. It means when you're all finished, how much do you have? So they just cheat here so egregiously. All right, anyway, that the net force acting on an object is equal to the rate. So it's not equal to the rate. It's equal to the net amount of momentum or force that hits you. So it's just silly. The net force acting on an object is equal to the rate. It's not equal to the rate. It's equal to the total amount of force that affected you. All right, so anyway. at which its momentum changes over time. So it's not about the rate at which your velocity changes. It's about what's the total change in your velocity. So the net force is the total change in your velocity. It is not the rate at which your velocity changed. So it's just nonsense. Okay, if the mass of an object is constant, this law implies, I think he overtly stated it, he didn't imply it, that the acceleration of an object, so again, acceleration is just telling you the change in your velocity, and obviously if you're talking about a net force, then you're going to have to talk about the net change in your velocity, not the per second change, the net change, the complete change, the total change, is directly proportional to the net force acting on the object. So at least they're admitting that Newton said there's a proportionality between momentum and force. Is in the direction of the net force. So obviously this is where we're going to do this crushing thing, and this banging into two things banging into each other, and it's not going to be in the direction of any net force, in the sense that, yes, obviously if one object has more momentum than the other object, then the whole crash will move in that direction. So whatever object has the most momentum in a car crash, for example, it's going to move the crash in the direction it's going. All right, and it's inversely proportional to the mass of the object. So they're just saying that the two things are equal. Inversely proportional just means you lower the mass, the same effect happens. Half the mass, twice the velocity, twice the mass, half the velocity. All right, a modern statement of Newton's second law is a vector equation. So again, they're admitting this isn't Newton. Newton didn't write this. Newton didn't say this. Okay, and again, it's not the net force. The net force is the net change in your velocity. If you want the rate, which Newton drew an equation for rate, and the equation for rate is the change in your momentum over how much time, okay, and that would give you the rate at which you got the force. Not the net force. It would tell you like 9.8 meters per second. It would give you a rate that force is affecting you. All right, but if you want to know the net, the time factor goes away because the time is irrelevant. Time doesn't matter. All you're saying is what's the total change in your momentum? That equals the force. Time becomes 1. When you're using a net figure, time means the total time. So 1 unit of time is the total time it took. And it becomes a 1. 1 unit of total time. Okay, where P is the momentum of the system, they're just ruining the second. All this crap is not Newton. Okay, where P is the momentum of the system and F is the net sum, a vector sum of the force. So again, they're saying net force, and then they're going to use a rate, okay, of velocity, and that's not the net force. That's not the net momentum change. If a body is in equilibrium, there is zero net force by definition. So again, equilibrium doesn't mean anything, and zero net force by definition is stupid. So again, they're saying I could put a piece of steel in a vise and I can crank the vise down, and they're saying there's no force because nothing's moving. There's no pressure. So the surface of the vise and the steel there's no pressure happening there. The steel isn't under any pressure. Now obviously if it crushes something, then you can see the change, okay, but there's plenty of places where you're not going to see the pressure, right? Down in the ocean, you could go deep into the ocean, there's a huge amount of pressure. It doesn't look any different, okay, you can't see the pressure, all right, but there's a huge pressure difference. So why say something like this, there's a net zero force? There's no net zero force at the bottom of the ocean. There's a gigantic force. All right, net force by definition. Balance forces may be present nonetheless. So what does that even mean? Balance forces may be present nonetheless. There's no force, there's zero net force. So what's the point of saying there's zero net force if you want to imply there's no force? Of course there's a ton of force. It's just acting in opposite directions, and because either something crushes or it doesn't. If it crushes, it's obvious there was a force. If it doesn't crush, it's not obvious, but there's still plenty of pressure. In contrast, the second law states that there is an unbalanced force acting on an object. It will result in the object's momentum changed over time. So yes, you will see the motion. If there's a imbalance in the force, then it's going to be visible that the imbalance is there. It'll make itself more obvious. The pressure will make itself more obvious, okay, when you're actually moving something with it. But pressure is pressure, and every motion imposes weight, pressure on something. None of it ever cancels. It always has to be converted into some kind of work, and work like energy, like heat. Heat is work. Heat is a loss of your energy. It's a loss of your force. All right, in common engineering applications, the mass in a system remains constant, allowing a simple algebraic form from the second law by definition of momentum. So again, this isn't simple, and it's a perversion of the simple truth. So again, if you want to know, it's not the net force. So this equation, this is Newton right here. The change in your momentum, change in your total MV, okay, over the change in time. Now obviously that's a rate. And obviously if I'm doing net force though, if I'm saying I don't want the rate at which it's happening per second, I don't want to know how the force changed, I want to know the net amount of force applied, then you just cross out this t. It's irrelevant. And all you say is change in momentum. That's Newton's real physics. Where m is the mass and v is the velocity. If Newton's second law is applied to a system of constant mass, obviously, m may be moved outside the derivative operator and the equation becomes, okay, so now they're just saying the change in your velocity is the same as your change in your force. And again, it doesn't matter. You don't need delta t if you're saying net force. If you want to know the rate of change, then you leave the t there. If you don't want to know the rate of change and you just want to know the net change, you get rid of the t. That's the fair, accurate mathematics. So they just cheat by presuming they're going to tell us the net force by telling us the rate of change. The net force will not be told by the rate of change. By subtracting the definition of acceleration, by substituting, the algebraic version of Newton's second law is derived. So again, we know this isn't Newton's. If Newton thought this was a rational way to treat his argument, he would have done it. So he didn't do this, okay? Because I would argue, I mean, even if he did this, he certainly knows this a, okay, doesn't mean a squared, a per second. He certainly knows that he wouldn't put a square on that a. All right, so third law. So they don't overtly say 1/2 mv squared, but they're trying to say Newton said 1/2 mv squared when he certainly didn't. Okay, third law. Whenever one body exerts a force on another, the latter simultaneously exerts an equal and opposite force on the first. So this is just sort of wrong. All right, so I would say that, okay, Newton, this is all verbiage, and, lots of arguments can be made about how to best state something. But that's really, there's no counter force. If I have $10, I have 10 force, and I give away 5, there's no counter force that makes me only have 5 now. There's no counterforce that took the money from me. I gave it away. If I give away the $5, I only got $5 left. They got $5. The force is conserved. The money's conserved, but no one took it away from me. There was no opposite force that made me poorer. My action of giving it away made me poorer. And so I think it's a fair distinction, that there's no opposite force. There's just the one act of you giving it away. That's all you need. The one action of giving your force away already makes you poor. All right. In vector form, if F whatever is the force of a body 1 on body 2 and F2 that body 2 on body 1, then so again there is no counter force when things exchange. There isn't, especially the Newton's cradle kind of shows it. I mean, the one ball goes in and the force just slides right into the other one. There's just absolutely, it's seamless. There's no counter force stopping this one. It's just that the force slides right out of it into the other object. All right. This law is sometimes referred to the action-reaction law, F called action and F2 called reaction, whatever. Newton's third law is a result of applying symmetry to situations where forces can be attributed to the presence of different objects. What it's saying is, okay, it's just the conservation law. Yeah, it's just basically saying that you can't make something happen, okay, without making something happen in the other side. My wallet can't not change if I take a 5 out and give it to somebody else. My wallet changes. All right, so the universe acts that way. So if there's something in the universe going this way, there has to be something else in the universe going that way. It just has to add up. Explosions create it all, right? So the explosion has a piece going that way and a piece going that way. The expansion has a piece going that way and a piece going that way. The retraction, the compression has a piece going in and a piece going in the opposite way. And that's what the universe is. The universe is compression and expansion. All right. Newton's third law is a result of applying symmetry. Okay. And thus, there is no such thing as unidirectional force. All right. So we'll probably have to deal with that. The third law means that all forces are interactions between different bodies. And thus, there is no such thing as a unidirectional force or a force that acts only on only one body, that acts on only one body. So of course the action is clearly, again, the bullet doesn't, there's no counter force that takes the energy from the bullet. It's all an action by the bullet. Anyway, in a system composed of objects 1 and 2, the net force in the system due to their mutual interaction is 0. So again, this idea that net forces, the two forces in opposite directions have no energy is retarded. So obviously the energy, if there is an action, okay, if you don't just you have two arrows here and you could say, okay, they cancel. No, they don't. And when they hit, they're not going to cancel. All right, if they're elastic, they're going to reflect. And you're still going to have the same amount of arrow. And if they crush something, you're going to use these arrows and you're going to make a bunch of little arrows. So there is no such thing as canceling. Two forces equals pressure, not 0. So if I apply the two walls are moving in towards you, you know it's not 0 force. I mean, this equation is basically saying, look, the two walls are moving in, it's 0 force. It's clearly not 0 force. The net force is going to be huge. You're going to get crushed. All right. More generally, in a closed system of particles, all internal forces are balanced. They're stuck with the amount of stuff that's going one way or the other way. So the argument is if I had a bunch of BBs, and even one of the BBs, there was one more BB to start with going this way than going that way. Let's say they can only go 2 ways, just to make it simpler. The BBs can only travel 2 ways, this way or that way. So I have a system and I start right now. The system starts. And I have one extra BB going this way. The fact is the whole box is going to slowly move in that direction forever because of that one extra BB. And because it always conserves. You can't get rid of that fact that you have one extra going this way. And so even though it'll stop and go and stop and go and stop and go, it's going to keep going forever. All right. So the particles may accelerate with respect to each other, but the center of mass of the system will not accelerate unless there's an uneven force to start with. So if it's a balanced force, if just as many are going this way as going that way, then the system isn't going anywhere. So it can jiggle, but it won't go anywhere. All right. If an external force acts on a system, it will make the center of mass accelerate in proportion to the magnitude of the external force divided by the mass of the system. So it's just saying if I add one more BB, even from the outside, I hit the walls and actually make the walls start to move. The whole system has to move. Okay, so anything I introduce from the outside will destroy the balance and just be like me adding a BB. So any bumping I do will just create essentially new BBs in the box, moving in one direction rather than the other direction, and I'll just ruin the balance that did exist. Combining Newton's second law and third law, it is possible to show that the linear momentum of a system is conserved. So again, they're saying it overtly, and yet they don't believe that you have to conserve linear momentum. They believe that two cars can crash, okay? I have momentum in two directions. I have a force going this way and a force going that way, and somehow they don't have to reflect with that total momentum. I can destroy some of it somehow. In any closed system, in a system of two particles, P1 and P2, momentum of vector 2, then blah, 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 blah. So again, they're playing with this zero term, which means they're pretending that two forces, two walls coming in is zero. And then they're saying, well, if I make one wall come in at 1 mile an hour faster, that now somehow the net system is 1 mile an hour. When no, the net system is the pressure plus the 1 mile an hour. It's not you don't subtract the total force. You're increasing the pressure. You're not decreasing the pressure. Any extra motion I give to one wall, I'm just increasing the pressure that the two will create. I'm making more energy. And if I had it one move slower, well, then I can reduce the energy. But I would never call the equilibrium zero, because the equilibrium isn't zero. All right, defining force. Well, this ought to be ridiculous. Let's see. Some textbooks use Newton's second law as the definition of force. So they use, it's not Newton's second law. So Newton's second law is the net change in force is the net change in momentum. That's Newton's second law. However, the equation F equals ma, which isn't Newton's equation, for a constant mass m, and then to have any predictive content, it must be combined with further information. So this is their excuse to say, we can't solve the equation unless we create another equation, okay, and force them to, breed and create a bastardization of a truth. So they combine momentum and 1/2 mv squared and call that a rational equation when it's not rational. The two equations have a different answer to the same question. You can't combine the two words yes and no, okay? You're not going to get anything. You're not going to get the right answer. One of them is right and one of them's nonsense. All right. Moreover, inferring that a force is present because the body is accelerating. So again, all this crap about accelerating when all we're really talking about is a velocity. That's what momentum is, a velocity. Is only valid in an inertial frame of reference. So more nonsense about where you're looking at it from, which makes no difference. Okay, the question of which aspects of Newton's laws to take as definitions and which to regard as holding physical content has been answered in various ways. So who would even ask that question? What ways can we pervert what Newton said? Why would anybody even try to do that? Why not just take it as a fact and then prove where it doesn't get the right answer? So why don't you show where momentum gets the wrong answer? Show where Newton got wrong answers. Oh, that's right. You can't show where Newton got wrong answers. And the only place they do play with is the idea of, mercury processing. And Newton didn't get a wrong answer if Newton's assumption that the sun isn't itself processing is inaccurate. I mean, Newton couldn't know that for sure, could he? No. So he didn't really get a wrong answer about how gravity works. He got a wrong answer about how the sun works. Which ultimately do not affect how the theory is used in practice. So this is just all babble, excuse making for we're going to completely change what Newton said. Okay, but we're not going to say that's what we did. We're going to do this gibberish instead. Notable physicists, philosophers, and mathematicians who have sought a more explicit definition. Now, you can't get much more explicit. Twice the force, twice the velocity. 3 times the force, 3 times the velocity. Can't get much more explicit. I mean, pretty much said overtly, force equals momentum. Can't get more explicit, and they're pretending they need something clearer. All right, definition of the concept of force include Ernest Mach, who really was ridiculous. Even Einstein got fed up with him. and Walter Noli, whoever the fuck that is. So this guy means something to me. All right, I'm supposed to think this guy knows the truth. Wikipedia says this guy has proven himself an authority. So I guess we should find out who this guy is, right? So let's see. Walter Noll was a mathematician and professor emeritus at Carnegie Mellon University, a university known for flute playing. He is best known for developing mathematical tools for classical mechanics, thermodynamics, and continuum mechanics. So somehow this guy you need a link to. We need a Wikipedia page for this guy, because the editors of Wikipedia say so. Not because there's any good reason to think so. Alright. Forces act in a particular direction and have sizes depending on how strong the push or pull is. So again, they're kind of ignoring the whole idea of interaction here with pushes and pulls. But obviously it's a push-averse. I say obviously. I don't know how you can even think it could be a pull-averse. That there's some elemental pull force. How would that be manifest? All right. Well, anyway, combining forces. This is just about interaction. And again, they're going to argue that you can subtract momentums. That somehow you can make a momentum disappear, okay, magically. Like it actually does, counteract. That it just, two forces go in, only one force comes out kind of thing. Can't happen. Alright, so this is probably enough of a video, so maybe we'll save this section for a next installment. Yeah, maybe. I don't think it's going to be all that interesting, frankly, but we'll get to it. Alright, so we'll call that a video. And say shit. It's a stupid averse. It's just a nonsense averse, a fable averse. People just will not, see any reason to stay grounded in something real. They always have to reach for, Star Trekian perfections or something. I don't know. Just wooey bullshit. Just very tragic.